All right, welcome. We made it through another week. There is a kappa set that's been posted this morning. That kappa set will be due at the new normal time next Thursday in preparation for the exam on Friday. Next week will be an unusual week. It is, let me go back to the kappa set. It's only 7 questions, so it's kind of a half kappa set from usual. And I think we'll get through today everything you need to do the kappa set. So there's no reason to put it off really at all. It will involve a couple of problems that involve you having to solve a numerical equation. We're going to talk about ways to do that, hopefully by the end of class today. But it won't just be, some of the questions will be more difficult, not more difficult, but you'll solve them in a way that you haven't ever solved perhaps a problem for. So that'll be fun. There is a reflective writing question that I'm crafting relating to the first exam, which I may want to have do earlier than the normal Friday, just so you can have some time to think about it. I will send an email about that when the time comes. You just got word today, I just got word today that we are entirely online after Thanksgiving. That is kind of out of the blue to me. I would assume that we were just things were going pretty well, that we would just continue on to the end of the semester, but apparently that is not the case. So I have to rethink a few things about how we're going to do the end of the semester. Obviously, I'll be posting, well, I'll probably be asking you some questions about how you would want to proceed after Thanksgiving as we go along. There's a couple of options we have. We can do everything asynchronously. I can just post some lecture videos. You can watch them on your own time, and ask me questions then in Zoom office hours or by email or whatever. Or we can try to keep things synchronous, meet at the same time, do a full 50 minutes, sort of give you a chance to interact with me at some level. So I'll probably poll you at some point to see what your preferences are, ask you for your opinions about how things can work. Obviously, you've seen that happen. It's only the very last quarter of the semester, so it's not like we're losing half the semester. But there's some cool stuff at the end of this class that we'll be talking about, like special relativity and things. Yeah, I don't want that to get lost. It won't get lost. We'll make sure it doesn't get lost. But we will need to find a way to have an engaging last quarter of this class, even so. So we've all been through this at some level. I have some things that I think will work, but you may have some ideas also, and I'd be very interested to hear what ideas you have. I'm also not entirely at all sure how the 4th exam will work. No idea. I'll be thinking about that for the next few months. So we'll talk about that too. But either way, we'll get through it. It's just slightly different way than we're doing it now. I owe you an equation sheet for exam 1. I'll be posting that this afternoon. Any other questions or concerns? Yeah. That's a good question. Am I still holding office hours next Wednesday? As you know, next Wednesday is Rejuvenation Day. I hadn't really thought about it. Would you like me to hold office hours next Wednesday? I probably could. Okay. I'll plan to hold office hours next Wednesday. I probably won't be in the office, so don't stop by, but I will be available for Zoom questions between 9:30 and 11:30 next Wednesday. There won't be a practice exam. The homeworks are pretty good indication of the kinds of questions I'll be asking, although there may be some more conceptual questions as well. They won't straight be homework questions, but they'll be similar to homework questions. So. Other questions? Yeah. There was an email that I got today. I assume that students got it also. Yes. Talking about the change in online. Yeah, it was from the president's office this morning. Ah, you haven't been able to check the email today. It's sitting there waiting for you to look at it. Right, about housing choices and preferences. I guess there is a possibility of staying on campus if you're already on campus, but I don't know how long that works. So you'll have to work that out. Other questions? Okay. Then let's go ahead with deriving the intensity profile for the single slit. That's what we were in the middle of, or at the very beginning of, in class on Wednesday. Just to remind you where we were, this is a slide from last week, or from yesterday or from Wednesday that I didn't really get to all that much, but it is the kind of the picture to remind yourself what we're looking at. Very similar. You're not seeing anything. Zoom people are seeing anything. You guys are not seeing anything. Now you're seeing things. Okay, good. We've got a single slit. We've got some, with A, we've broken that up into an arbitrary number of, in this case, you can see 4 different rays, all with some angle. This angle theta is going to become important now. We're going to need to be thinking about what this angle theta is. When I say angle theta, there's a lot of angles we're going to be talking about, but theta is the angle between the line between the slit and the center of the screen and the actual point on the P on the screen that we're interested in knowing the intensity of. Okay, that's what, when I say theta, that's really what we're talking about. And we are now going through the exercise of thinking about, okay, 4 slitlets is good, 8 slitlets is better, but maybe we can make them really, really, really small. Maybe we can call that dx instead of a over 4. And maybe now we can get down to solving some really interesting things. So let's go back to today's. Okay, and let's go to here. And let's remind ourselves where we were. So each one of those little slitlets we had written down, we had drawn anyway. Close the attendance thing. There we go. You can go over here. Go over here. Okay. Click back in here. I finally figured this whole crazy setup up here. Anyway, we've got our phaser. Oops, that didn't work. Uh-oh. My buttons aren't working today. Why is that? I don't know. Okay, that seems to have done anything. Okay, let's do it. Here's our phasor diagram. And we know that each one of our little phaselets, so again, remember what we've done. We've broken up, we want to now combine each of the phasors from each of those individual slitlets. And each of them are going to have a very slight change. It's going to have a very small amplitude, and it's going to have a very small change in phase from the one immediately above it. And so we visualize that by a bunch of I didn't draw them very small so we could actually see them, phasors, the first one being arbitrarily at 0, the next one being a little bit above, a little bit above, a little bit above. All of these phasors now we're going to add up in some sort of geometric pattern, which as we make dx smaller and smaller, is going to look more and more like a arc of a circle. That's what we're doing here. So take those ones that I've just drawn, and you're going to get something that looks like this. And as we make those things smaller and smaller and smaller, you're going to go from some polygon form to an actual circle form. And that's where we're going to be. Okay, now how does changing the wave changing theta affect things? So now I want to change, we were here yesterday. Now let's change theta. Let's move to a different point on the screen so that that angle changes. Maybe we start at 0 and move up. What is that actually going to be doing to these phasors? We see how changing the x changes things. How does changing theta affect things? As theta goes up, delta L, which is the path length difference between adjacent slatelets, is going to get bigger. And so delta phi, which is the phase angle between adjacent slitlets, is also going to get higher. The total phase difference is going to get bigger. Delta phi is the angle between successive phasors. So let's start with the simplest case. Let's start with theta equals 0. What is the theta equals 0? What is that? What point on the screen does that physically represent? The center point. Where should that be on the diffraction pattern fringes? That's the center point. That's the maximum. It should be at the maximum intensity there. So what is that going to look like? So at theta equals 0, what are all these delta phi's? Assuming that the slit width is much smaller than the separation, let's say, between the screen and the slits themselves. It'd be 0, right? They're basically all lined up. They all have exactly the same phase. They all have exactly the same distance to get there. There's no delta L between. Delta L is 0. And so, I mean, within the approximations of this being very large, all these delta phi's are 0. What does that look like on our phasor diagram? That's easy. I can do those phasors in my head. All of these phasors have delta phi equals 0. They all point in the same direction. Right? Okay. What is the total length of this new phasor? Well, I don't know, but let's call it Emax. Remember, we're really talking about combining the electric fields of all these different individual phaselets. We're talking about the new component of the electric field. The new amplitude of the electric field is just going to be the sum of all those individual phaselets added together. Okay, that vector diagram is easy. They all add together. Okay, so as theta increase, that's the uninteresting point. Let's do some more interesting points and see what's going to happen. As the angle increases, as theta increases, we know that delta phi is going to increase. I just wrote this down. Do the lengths of the individual phasors change as I move up the screen? They do not. That Emax, the length that we got for that Emax, the sum of all those individual things is still going to be the path length that these phasors take through phase space. Always. Doesn't matter where we go on the screen or what theta is, that path length is going to be the same. Lengths of individual phasors is the same. So total path length is still equal to Emax. Okay. So, but as theta goes up, we have some different geometry going on. So, for instance, but the length of the sum will change. So let's talk about, again, if you have enough of them, you're going to get an arc, a piece of a circle, right? Depending on what that theta actually is. So the total electric field amplitude will be smaller. This will be the sum of those phasors. The arc length will be still Emax, but the length of the new phasor will be less than Emax. Just how we're coming down on the diffraction pattern. Okay, so we get the arc of a circle. So this length is still Emax, but this is less than Emax. And now our job is to figure out what that is. Okay, so how much of a circle is this? So we need to know now how much of the arc of a complete circle we've actually subtended by this thing. How are we going to figure that out? Well, we're going to need to know some angles, like this angle. This angle, which I'm going to call phi, is the angle of the last phasor delta phi that I put in there. How far out of phase? Basically, it's the phase difference between the first one, which had phase angle 0, and the last one. So I can probably figure out what phi is, actually, because I can tell what the phase difference is between the bottom of the slit and the top of the slit. That's going to tell me the total phase difference between the first phasor and the last phasor. So this is the phase difference from one side of slit to the other. And we can probably figure out what that is. We've already done the geometry of this many times. This is just 2 pi over lambda times a sine theta. If you don't remember what the geometry is, draw the triangle again, figure out what your theta is, and solve that for your delta phi, for your total phi. Delta phi was our individual between slatedlets. Phi is going to be the total phase difference from one side of the slit to the other side of the slit. Okay, this is also the angle that's subtended by, get this now, this is where it gets crazy. This is the angle subtended by the circle about its center, right? We have a partial circle here, which is the arc. If we were to find the center of that circle somewhere, like up there, maybe, we could draw diagrams that look like that. And that angle, that phi angle that we just drew is also the angle, this angle right here. Yeah. How do we know what theta is? We've picked it based on what part of the wall we're thinking about. Right? So it's arbitrary. We haven't defined what theta is yet. I have drawn a particular value of phi, so that's going to give us a particular value of theta. But we're going to, that's just a particular one. We're going to relax that in a bit, and we'll be able to use any value of theta we want to, which will give us any value of phi we want. But I've drawn down a particular one just so we can see what happens. Okay. So that's a little bit of a stretch, but it should follow that whatever fraction of the way around the circle we've gotten should be the degrees that angle actually is. And those two angles are exactly the same. Oh, it's also the arc length around the circle. So we know that, we can define now some R variable. Let's say R is the distance from the origin to the center of our circle up there somewhere in this weird phasor space, right? And we know that this arc length is EM. we can start figuring out what these angles and geometries and other things actually are. So keep this picture in mind. I don't have enough board space to have it up and both do math, but if you need me to come back to it, I'm happy to do that. Okay, so some interesting things. We know that R times this phi vector, phi angle, is equal to EM, right? This is just the radius times the angle gives you the arc length. If the angle is in radians. That's why why we use radians, because it makes this formula work. This is just arc length formula. So we can figure out what R is. R is just EM divided by phi. That's an equal sign. Okay, now let's break this triangle, now let's break this arc up into two. Let's draw a divider right down the middle. And now we've got two right triangles. What are we really interested in? We're interested in figuring out what the length of this arc, of this new phasor is. That's what we're really interested in getting, because that will give us the amplitude of the new electric field, and that squared-ish will give us the new intensity. And that's really what we're interested in, the intensity. So we need to know what the length of that arc is. We can get that by splitting this up into two right triangles and thinking each of them has angle phi over 2 up here. We know what R is. We should be able to figure out what that side is. I'm going to draw that triangle down here. This is the right triangle that I just drew. We know that this angle is phi over 2. We know that this is R, and this is what we want. This is E, the electric field amplitude at that particular angle divided by 2, right? Because it's only half of the way across the whole thing. E theta is what we want, but we have everything we need now because we know what all these other things are. So we know that the sine of phi over 2 then is equal to opposite over hypotenuse. That's E theta over 2 divided by R. Let's solve this thing for E theta. E theta is 2R times the sine of phi over 2. And if we want to plug in what we know our R isn't anything physical anyway. Let's plug in R in terms of what we had done in terms of physical things, EM over phi. Then we get E is equal to 2 E max over phi times sine of phi over 2. Okay, let's make some, so that's really it. We've done it. That gives us the electric field. We're basically almost there. And it only took us the geometry of the phasors and not any crazy trig function. So this is the power of phasors. Let's set alpha. This is what's normally done. We're going to define alpha to be phi over 2 or pi over lambda, sorry, times a sine theta. Because theta, phi, remember, itself is just 2 pi over lambda times a sine theta. So if we set alpha equal to phi over 2, this becomes even simpler. Because there's a phi over 2 in both of those inside and outside of the sine function. This just becomes E of alpha, E of theta, equals EM over alpha times sine alpha. Okay, intensity, we know is proportional to E squared. So the intensity as a function of angle, which is really what we want, is some I max, which we don't care, well, it's just there, it's the intensity in the center, times sine of alpha over alpha, quantity squared. Yeah. I is proportional to, intensity is proportional to the electric field squared. That's what I've written there. So there's some other constants in there, but it doesn't really matter because we're taking whatever the Emax was and converting whatever to the Imax is. And so those constants just get shoved into converting E's into I's. We don't really care about them. Yeah. Imax, that's exactly right. Imax is defined to be the intensity at theta equals 0, the intensity at the top of that intensity profile, which is different than I naught of the double slit profile, because I naught is this is where the definitions get a little bit tricky. I naught has some physical meaning in the double slit formula, and that physical meaning is how bright a single light source would look at that particular spot on the screen. That is not really a thing here anymore. All we really care about is Imax, and that's why there's a 4 here in the double slit formula where there's not a 4 here in the single slit formula, because Imax is a different, slightly different definition than I naught. Good clarification. Okay, so remember that alpha equals pi a over lambda times sine theta. So we've got the same sort of thing going on again. We've got a sine function inside a sine function. Same sort of thing we had going on with our double slit formula. When is you're going to do this? When is your double slit interference lab? Is that coming up sometime soon? Does anybody know? Usually it's done kind of now-ish in the semester, but this is a weird semester, so you'll get a lot of, you'll have a lot of fun using solver to solve this particular pattern with all sorts of other things going on. Anyway, I'll let lab people worry about that. Okay, so right, IM, we don't really care what IM. It is the value of the intensity at theta equals 0. It is I at 0, because this whole term goes to 1 at theta equals 0. Interestingly, even though both the top and the bottom go to 0 sort of simultaneously, the whole thing goes to 1 at I equals 0. Okay, so as theta gets bigger, we've done a single value of theta. As theta gets bigger, but this is a totally general thing. What happens in the phase diagram as theta goes up? Well, we did a rather small version of theta. What if theta gets pretty big now? Again, here is a small version of theta. As theta gets bigger and bigger, this thing just gets wrapped tighter and tighter. And I'm gonna have a hard time. That's a terrible circle. These need to all be segments of circles that all have the same arc length. Right? It's gonna start wrapping around on itself. The bigger theta gets, the more this thing wraps around on itself. But again, the final intensity is due to the electric field, which is going to be the distance between the origin and wherever this thing ends up being ending. And that's going to get closer and closer to the origin as this thing gets wrapped further and further around. In fact, there's going to come a point when that meets all the way back at the beginning and we're back at 0. And that's our first minimum point. It defines the entire circle. and comes back to the origin, and the length of that new phasor is 0. That's our first minimum point. And then you start wrapping around more than once. And it gets bigger again because you've wrapped around and now left the origin, and you've got some non-zero function there again. This is done better in this PowerPoint slide. Here are some better diagrams from the book that show how this works. That's a better diagram than the one I drew, but it shows the geometry just the same as I drew it here. Emax being the same between both of those, but the E theta being a little bit smaller for this particular value of 5. And here is a nice diagram that shows the entire first 3 minima of the interference pattern and what those phasors look like when they all get added up in those particular spots, right? Here is the center. They're all lined up. You get your maximum intensity. Just a little bit off of that, you get still a pretty high intensity, but not quite as big as it was before because they're off curved in an arc now. This first minimum point is the point at which they're all exactly looped back on each other to get back to the original starting point. This point, the first intensity, the second, let's say they have the central maximum, the first maximum on either side, where does that happen? It doesn't quite happen at 1.5 loops, because every time you make the loop a little bit larger, again, you're taking the same size string and looping it more and more. And so to get all the way to 1.5 loops, you're making the circle that you're making smaller and smaller and smaller and smaller. You can kind of see now why it is that the intensity maxima don't quite happen exactly halfway in between the intensity minima. It's because you're taking this loop and you're making it smaller and smaller and smaller. And it happens to be that at the point at which this is maximum between these 2 minima happens to be a little bit before you get all the way around to the top again. Because there's some interplay between making the phasors get all the way to the top and making the thing get smaller and smaller and smaller as you do. So that happens a little bit before then. And so this is a little bit asymmetric. But by the time you get down here, you've looped around twice. By the time you get to this minimum, you've looped around 3 times, and you're getting less and less separation between the origin and these things, which is why these peaks get smaller and smaller and smaller as you go up. That's a terrible drawing. Hopefully it makes some sense. I apologize. My feeble drawing skills have been laid bare. Okay. Let's look at the whole single slit pattern. That's not bad. That's one of my better single slit pattern drawings. I'm pretty good. So this was very useful, and it was very useful in the homework this week to be able to look at this and say, okay, m equals 0 is at the center. For the double slit, m equals 1 is the first maximum, m equals 2 is the second maximum, m equals 1/2 is the first minimum, n equals 1.5 is the second minimum. To have that picture in your head. Let's try to draw a similar picture in our heads and have a similar picture ingrained in our brains of what this looks like for the single slit pattern. And we've got lots of different things to think about, right? There is certainly still m, and the m values are not that dissimilar to what we had before, except it's 0 at the center, and we know that m equals 1 at the first minimum, and 2 at the second minimum, and 3 at the third minimum, right? In our m lambda equals a sine theta calculation. This is -2, -3. I'm in some, what? Oh, what? That was the weirdest thing I've ever seen happen. Go away. I wanted to make these next. Not gonna. Does this button work now? I've gotten some weird state here. Hopefully this is going to give me back control. Yes, that's a negative sign. These are negative signs. Okay, those are our m values for m lambda equals a sine theta. What other things? Again, we talked about alpha. Alpha is again, phi over 2, still 0 at the center, but it's going to be, this is going to be alpha equals pi. This is going to be alpha equals 2 pi. This is going to be alpha equals 3 pi. You can probably guess what these are. For phi, this shouldn't be too hard to do. You just have to multiply all of those alphas by 2. This is alpha equals 2 pi, 4 pi. So phi equals 2 pi, 4 pi, 6 pi, right? It's 2 pi all the way around a circle once. So if you want your phase difference to be a full circle to get back to 0, that's a full 2 pi around. And that's how you're getting phi back to its starting point. Now you're 2 pi, negative 4 pi, negative 6 pi. How about theta? This is really the physical thing that you're looking at. The angle between the slit and the point on the wall that you're talking about. And these are, again, inverse sine of lambda over A. This is inverse sine of 2 lambda over A. Inverse sine of 3 lambda over A. You get the idea. Where am I at on top? Okay. And this is similarly inverse sine of negative lambda over A, et cetera, et cetera, et cetera. I'm not going to write all that out. You can fill in your notes to make it go. Okay, so if ever you're thinking of, and this is a useful chart to keep in mind, and if you're ever wondering, okay, alpha equals this, what the heck does that mean? You can refer to this chart. Alpha refers to a specific point on the interference diffraction pattern. M refers to a specific point on the diffraction pattern. Phi refers to a specific point on the diffraction. Theta does not. It's going to depend on what lambda and A are and the ratio of lambda to A. But you can convert that into an alpha, theta, or M and figure out exactly where you are on the interference pattern itself. Okay, now let's go ahead and find where the maxima are. Where are the maxima? We have enough information to do it now. Where are the maxima of the single slit besides the central one? That's easy. Where are the other maxima on the single slit diffraction pattern? Where are the maxima? So we've got I equals IM times sine of alpha over alpha squared, where alpha equals phi over 2, and that equals pi over lambda times sine theta. Draw that very well. Can't erase it. Okay, this is pi over lambda. Okay, great. So how are we going to find the minima? What mathematically do we have to do? Take a derivative and set it equal to 0. Okay, with respect to what? What? Theta? Yeah, we could do that. In fact, we could do it with respect to theta. We could do it with respect to phi. We could do it with respect to alpha. It doesn't really matter. We can do it with respect to any of these things. And alpha is going to be a whole lot easier. So let's do it with respect to alpha. You mind? Thanks. So take a derivative and set it equal to 0. We know the minima are at m lambda equals a sine theta. Okay, so let's just take the derivative of this and set it equal to 0. I'm going to write it out what the derivative of this thing is. It's kind of messy. If there are some derivative aficionados in the audience and you'd like to check my work, please feel free to do so. But basically, I'm using the chain rule a couple times. In fact, the chain rule is all you ever really need to know if you want to take derivatives by hand. The chain rule, you can derive any other rule, quotient rule, multiplicative rule, by the chain rule. So if you only know one rule, and I only remember one rule, it's the chain rule. That's the important one. Okay, so di d alpha is equal to Im, and the chain rule says I have to take the basically the derivative of, treat this as an x squared, and that becomes 2x, 2 sine alpha over alpha, times the derivative of the inside. Okay, so this is times derivative of the inside, which is going to be the derivative of the sine alpha part, which is going to be cosine alpha over alpha, times or minus plus the derivative of the bottom part, which is just going to be 1 over alpha squared times the negative 1 sine alpha over alpha. That look reasonable? Are there some derivative aficionados in the audience? Maybe there are. Yeah? Do you like it? Are you okay with it? You don't like it? Yes, you're right. Thank you. Absolutely right. Thank you. No, it's not. Yep. Well, I wasn't right before, so I think this is right, but check me. If I'm not right, you can let me know. Okay, so this gives the minima and the maxima, though. How do we know which is which? Well, we can probably figure this out. Which is which? So this is all set to 0 when one of two things happen. Either sine alpha over alpha is 0, or this thing is equal to 0. One of those should give us the minima, and one of those should give us the maxima. So let's try the easy one first. Sine alpha over alpha equals 0. That's certainly going to work. What does that lead to? Well, you can multiply both sides by alpha. You get sine alpha equals 0. And we know that this happens at alpha equals 0 and pi and 2 pi and 3 pi, et cetera, et cetera, et cetera. That we know are the minima. So we've successfully found that works. Alpha equals pi, that gives us the minimum one. So this gives us the minimum. It must be that this one gives us the maximum. So the maxima then must occur at cosine of alpha over alpha minus sine of alpha over alpha squared equals 0. Okay, we can just solve for alpha now and figure out where this thing actually is. This is cool. So cosine alpha over alpha equals sine alpha over alpha squared. That's one. Multiply both sides by alpha squared. Divide both sides by cosine. We get alpha equals sine alpha over cosine alpha, or alpha equals tan alpha. Okay, now what? This is what we call in the business a transcendental equation. This cannot be solved analytically. You have an alpha on one side, a tan alpha on the other. There's no way to solve for alpha here in any sort of analytic way. You have to solve these things numerically. You have to solve numerically for where tan alpha actually equals alpha. There are lots of ways to do this. I suggest that you use one. Have you learned solver in lab yet? No. You're going to be learning solver soon. You can do this in Excel, right? You can have a cell for alpha and a cell for tan alpha, and you can slowly change alpha until the tan alpha thing agrees with it, right? That's the simplest way to do this in Excel. It's kind of painstaking because you have to slowly iterate on getting closer and closer to tan alpha equals N alpha. If you know how to use solver, which you'll learn hopefully in the next week or two, then you can do this. It will do that iteration for you. That's basically what solver does. It iterates until those things happen. But I can do it in Mathematica fairly simply. So let me show you Mathematica. That's not Mathematica. Let me show you Mathematica and just show you what this looks like, right? So I'm going to plot, make this bigger so you can actually see what's going on. Yeah, 300%. Oh yeah, that's good. Plot alpha I can even if you don't know Mathematica, it's okay. You'll actually learn it in Math Methods next semester. And I want to go, so I'm going to plot alpha and tan alpha as alpha goes from, let's say 0 to, I don't know, 6. Let's see what happens there. Okay, cool. Make this a little bigger so you can actually see what's going on. So I've got two things plotted here. The blue line is alpha, and the orange line is tan alpha, right? So you can see where this actually happens. Obviously, they're equal to each other at the center. We get a nice maximum there. But the next time they're equal to each other isn't until out here at like 4.4 and a half or so, right? Let's zoom in on this crossing right here. Let's go from, instead of going from 0, let's go from 3 to 5 so we can actually see what's going on. Aha, it looks like it's right about at 4.5. Maybe it's exactly 4.5. Wouldn't that be nice? Now I can, how much time do I have? 2 minutes left. Do I want to try to do this in Excel? I want to try to do this in Excel. Sure, let's try bringing up an Excel window. That's not the one I want though. That's a different Excel window. Okay, let me make this really big so you can see what I'm doing. So I can say, make this 200%. Okay, so I can have it called alpha and tan alpha, and I can do this. So let's call this 4.5, and let's call tan alpha tan of equals tan of this. Okay, and you can see that we're close, but we haven't quite gotten there. And again, this is in all in radians. So I can now go through an iterative process. I can say, okay, I need to make this a little bigger. How about 4.52? Holy moly, that was weird. I actually need to get smaller. How about 4.49? I've actually overshot already, right? So raising alpha makes my tan alpha go a little bit lowering this made this get too small. So it's somewhere between 4.49 and 4.5. And now I can start iterating until I'm all done. There is something let me just show you how this works, because solver is really important and useful here. I'm almost out of time. But if you go to data, solver is actually an add-on, and sometimes it'll depend on whether you're using Windows or Mac, how you turn these on. I can, for instance, go to data, tools, Excel add-ins. I think if you're on a PC, you have to go to like the file menu, but there's an Excel add-ins menu somewhere, and you have to click the solver add-on tool. It's already in here, it just doesn't show up by default. But once you have that solver thing in there, you can turn solver on. And you can say, I'm gonna click on this cell, I'm gonna click on solver, and I'm gonna say, you can't really see this, sadly, because it's so tiny, but I'm gonna set my objective, which is this cell, to be tan alpha, and it's gonna say, what do you wanna do? Well, I want to, actually, need to do one thing first. I'm gonna say the difference, this is gonna be the difference. I'm gonna make a diff cell equals the difference between alpha and tan alpha. And that way, I can make this my target cell, and I can say, make that go to 0. When the difference is 0, then those two things will be the same. That's actually a lot easier than making one thing equal to another thing. So I want to make that a value of 0 by changing the value of alpha. So it's going to change alpha. It's going to do this iteration for us. It's going to change alpha until the value of that difference cell is 0. And that should be the point at which both of these things are the same thing. I can say solve. It's going to chug away for a bit. Shouldn't take too long. It's going to ask me if I want to keep the solver solution, which I don't want to do because something went horribly wrong. Let's try this again. Solver. I want to change, I had the wrong, it took tan alpha to 0. I really want this to be C3. I want it to be this cell by changing A2. I think that's gonna work now. Value of 0. Okay, let's do it. I had the wrong cell there. Okay, now, it hasn't quite gotten to 0, but it's gotten to 8.8 times 10 to the negative 7, which is pretty darn close to 0. And you see, I've got two numbers here that are basically indistinguishable out to the 4th or 5th decimal place. And that's it. That's the answer to this question. That is where the first peak happens. It happens in an alpha value of 4.493. Okay, and we will, I'll go through the rest of these on Monday, but at least you have a sense now on how you can solve this transcendental equation, and you have the solution to the first value of alpha for this equation also. Have a nice weekend. We'll see you on Monday.